So I've written down the definition of a derivative, but to be able to take a derivative, we need to be able to take that limit. And we can only take limits at cluster points. Okay. Now, in the book, this is, by the way, this is section 6.1. In the book, they focus on intervals. So they always assume that the domain of the function is an interval. Now, if your domain is an interval, then every point in that interval is a cluster point. And so you can take a derivative anywhere on that interval. But I'm going to do it just a little bit more generally. I'm going to allow your domain to be an arbitrary set, and then I'm going to say that for us to take a derivative, it has to be a cluster point. Okay. So that's where we're going to start. That's our definition. Suppose we have a domain A. So it is a domain. That means F maps A to R. And let C be a cluster point of A. Then F is differentiable at C if that limit exists. And in this case, so if that limit does exist, then that's the derivative. So in that case, this limit is the derivative of F at C. And it's denoted, we're going to use the prime notation. The book seems to only use primes. It talks about the differential notation, but it doesn't seem to use it, so we'll go with that. Okay, so that is our big definition. Are there any questions about that? So we're going to spend only 2 or 3 lectures on derivatives because it's really not that complicated. Basically, everything you learn in Calc 1 is true, and the proofs of those things are not difficult. Okay. I mean, hopefully we have a little bit more rigorous understanding of limits now than you did in Calc 1. But the proofs are not difficult. Let's do a couple examples just computing derivatives from the definition before we prove any theorems. Let's let f of x be a constant. Let's let the domain just be all real numbers. And let's let C be anything. Okay, then what do we have? F prime of at C is the limit as x goes to C of f of x minus f of C divided by x minus C. Okay. That is the limit as x goes to C of a minus a over x minus c. And what is that limit?
Zero.
Yeah. 0. You might be a little bit worried about, if you look at this as a function, as x gets close to c, it goes off. If you ignore the numerator, it would be going off to infinity. But the point is the numerator is always 0. So at every point other than c, that thing is 0. And remember, in our definition of limit, we're not allowed to look at the point we're going toward. Okay. Okay, now let's move up to x squared. I hope you can see that if our function was x, then we'd get a derivative of 1. So let's do something a little bit more complicated. X squared will take our domain to be all the reals, and we'll let c be any point in there. Then f prime at c is the limit as x goes to c of x squared. Oh, yeah. We'll just start skipping a step there. X squared minus c squared divided by x minus c. And how does that fraction simplify?
X plus C.
Thank you. That does seem to show up all the time in this class. And now you see as x goes towards c, we're just going to get 2c. Good. Any questions so far? Okay. Let's move up to x to the n. N, a natural number. And let me actually say n is at least, I don't know, 2. Our domain will be all the reals, and we'll take any point in there. And we go and we compute the derivative. And we end up with x to the n minus c to the n divided by x minus c. Can anybody simplify that fraction? A couple ways to do it. One way is you can just do polynomial long division. Okay. The other way is if you know the answer, you can check it just by multiplying. So I'm just going to write down the answer. Let's pretend we did polynomial long division and we got this. Okay. Now, if you want to check that that really is the answer, multiply it by x minus c. Okay. So when you multiply by x, you're going to get x to the n plus c x to the n minus 1 plus dot dot dot. When you multiply it by c, you're going to get c x to the n minus 1 plus c squared x to the n minus 2, etc. But that c was a negative, and that's going to cancel all the terms. of the other one, except for the x to the n and the minus c to the n. Okay. What's the limit? I guess you can cheat because you know the derivative. But notice that each of those terms becomes a c to the n minus 1 in the limit. And if we count by powers of c, we go 0, 1, 2, up to n minus 1. So that is n terms there that are all equal to c to the n minus 1. Okay. Any questions? Let's do one more example from the definition. Let's do f of x equal the absolute value of x. Domain is all of R. And C is some real number. F prime of C is the limit as x goes to C. The absolute value of x minus the absolute value of C divided by x minus C. Okay, what's that equal to?
Three cases here.
There are cases. So first of all, if C is 0, this limit doesn't exist. Because if you come at it from the positive direction, you're going to get a positive 1. And if you come at it from the negative direction, you're going to get a negative 1. Okay, so there's two different ways to approach it, and you'll get two different answers, so it doesn't exist. On the other hand, if C is positive, okay, then how would you do this limit? You'd know that the absolute value, in this case, we're looking at the limit as x goes to c of absolute value x minus c over x minus c. Okay. You know that if as x gets closer and closer and closer to c, eventually x has to turn positive itself. And then you're just looking at an x minus c over x minus c, and your limit is 1. And the same thing if c is negative. Eventually x has to be negative, and then you're looking at minus x plus c divided by x minus c, so you get a minus 1. Okay. That's enough with computing derivatives from the definition.
Professor, quick question.
Yeah, go ahead.
So basically this result, it just follows almost immediately from the definition of the absolute value function.
Yes. We do have to think a little bit about those limits. The fact that if x gets close enough to a positive number, then it's going to be positive.
Mm-hmm.
So we showed that the limit at 0 doesn't exist because we can pick two sequences that will converge to 0, but the functional values won't converge to the same value.
Yeah, you can do it sequentially, or you can do it with the definition to the epsilon delta.
Okay.
For any delta that you pick, if you plug in x equals delta over 2, you'll get a positive 1. And if you plug in x equals minus delta over 2, you'll get a negative 1.
Okay.
So for any delta, you get two different answers. Therefore, you can't have a limit there. Okay. Now, as you can see, we're not going to worry too much about this. I've defined derivatives, right, where C is a cluster point of our domain. As you can see, that's not going to come up too much. But it's worth keeping in mind that we have to have that, or else we're not going to be able to take a derivative. Okay, a lot of results to state. Many of them we're going to breeze over because you already know them. Here's one you already know, but you might not have the proof memorized, and it's very short and it's something you should know. So we're going to have our standard derivative hypotheses. They are this. You've got a domain. You've got a function on the domain. And you got a cluster point of that domain. Okay, those are just our standard setting for talking about derivative. And now here's what this actually says. If f is differentiable at C, then f is continuous there. Okay, remember what continuity means. It means if we take the limit of f as we approach the point C, we'll end up with f of C. Okay, that's all it means. So let me compute that limit. F of x minus f of C. Okay. Well, we know that if two limits exist, then the limit of their product is the product of their limits. Okay? So now, because we know that f is differentiable at C, we know that this limit exists. Right? And the limit is x approaches C of x minus C also exists. I guess that's because C is a cluster point. Okay. And the product over here on the right is equal to the thing on the left because when we have two limits and we're multiplying them together, we can just take the limit of the product as long as all the limits involved exist. Okay. Well, on the right, we're getting f prime at C, but even more importantly, what's the limit as x goes to C of x minus C? That's 0. So we showed that the limit of f of x minus f of C is 0. Well, again, using the rules of limits, that means that the limit as x goes to C of f of x is equal to f of C, which is what continuity is.
So we can move these limits inside and outside of each other on the right side because everything's nicely behaved.
Yeah, if the theorem we're appealing to here is because both of these limits exist, their product is equal to the limit of the product.
Okay.
Okay. Now, time permitting, we have 3 more results to do. The first one is all the algebraic properties of derivatives.
Sir.
Yes.
So at the end, our final conclusion is the limit as x approaches c, left of x equals f of c. And why is that enough for us to conclude that f is continuous at c?
Because that's the definition. That's another way to write the definition
Okay,
of continuity.
Gotcha.
Okay. Madeline, no, you're not dumb. It's actually a reasonable question that Madeline asked in the chat. She says, how do we know this limit on the left exists? Okay. I guess I should have written these in the other order. Because we know the limits over here on the right exist. We know these guys exist. And that's how we know that the limit over on the left exists. Okay. The guys on the right, we know they exist. The first one because we assumed we're differentiable. And the second one because we assume C is a cluster point. Is that okay? Okay. Okay, so the algebraic properties of derivatives. I guess we'll call this a theorem. And we'll take our standard hypotheses, except we're going to have 2 functions now. Yeah, let's do 2 functions. So f and g both have domain A. And okay, algebraic properties of derivatives. The first one, constants come outside the derivative. Oh, I need another hypothesis. I need that f and g are differentiable at C. If f and g are both differentiable at C, okay. Now, this is the problem with the prime notation for derivatives, is it causes these things to be a little bit awkward. So if I take a constant a and multiply by f, and then take the derivative of that function and evaluate it at C, I get just a times the derivative of f at C. And that's for any constant a. Okay. Okay. Now we want to add. Okay, I hope everybody remembers this formula. Okay. Next, we want to multiply. Wait. Did anyone catch the really stupid thing I did here?
Isn't it just the sum?
Yeah. I just, there we go. I was ahead of myself, I guess. Okay. We'll take the derivative of the sum, it's the sum of the derivatives, and then we've got the product rule. Okay. Now what we're trying to do is just we want to get all the field operations in here. The first one gets us multiplying by a constant, so we can also multiply by a -1. Second one gets us addition and subtraction, because we've got the -1. The third one gets us products, and then to get quotients, really we only need reciprocals. Okay. So reciprocals, we want to be a little bit careful. This is like, we've done the same thing for sequences and for limits. So if f of x is not 0, on our domain A, then the derivative of 1 over f at C is negative the derivative of f at C divided by f squared at C. Okay. And so you combine the reciprocal rule that we wrote last with the product rule, and you can get the quotient rule that you know. Are there any questions before we prove one of these, maybe? I hope the proof of the first one with the constants is clear. You just plug it into the definition, you've got an A, the A's will just come out, okay? The second one, you plug f plus g into the definition, and then you'll just be able to separate the limit into two parts. You'll get both derivatives. The third and the fourth, they just require a little bit of clever algebra. So I'm going to show you the third, the product rule. And you'll get an idea for the algebra involved, and then you can look in the book for the reciprocal rule, okay? So let's do this. Proof of product rule. Okay, assume all the hypotheses and things. And what we're going to do is we're going to take the right-hand side right here, and we're going to do some slightly creative expansion of that, and we're going to end up with the left-hand side. According to we're going to end up with the definition of the derivative of the product. Okay? Let's see. And I realize in my notes I have this written the other way around, so I'm gonna change it to be f prime c g of c plus f at c, g prime at c. Okay. I guess I'm gonna have to come down here because this is gonna be a long line. Okay. Now, we're gonna have one creative substitution and two boring substitutions. The boring substitutions are the derivatives. I'm just going to write in the definition. Okay. Now, here's the creative substitution. Instead of g of c, I actually want the limit as x goes to c of g of x. Okay. That's the same thing as g of c because g is continuous. And g is continuous at c because g is differentiable at c, and we just proved that proposition. Okay. Now let's see, I'm going to put in, let's just put in the f at c, and then the definition of the derivative of g. Okay. Now, once again, we've got on the left half of this quantity is the product of two limits that exist. So the result is the limit of the product. Let's just do it as this. Okay. And then over on the right, there's not much to do. I'm just going to move that f of c inside the limit. And then since everything is a limit as x goes to c, I'll just put it all under the one limit. Okay. Okay, now let's just make it one fraction and see what we get. F of x g of x minus f of c g of x plus, oh, I wrote an f of a. I wanted it to be f of c. Okay. And then I get an f of c g of x minus f of c g of c. And then this is all divided by, both parts have an x minus c in the denominator. And you can see that magically these two terms cancel with each other. And by the definition of the derivative, well, there you go. Any questions?
understand why you have just f of c, and then I guess like why you have at first the limit as x approaches c of g of x, but then you just have f of c, and then the f of c is also in the limit. I guess I just don't understand that.
Yes, that's why I said there's a little bit of creative algebra. Okay? And there's a little bit of lack of symmetry that's kind of disconcerting, right? Because in the statement of the result, f and g play the same role, but then in the proof, we do one thing with g and we don't do it with f, right? Well, the thing is, if we replace that f of c with the limit, and we left the g of c as g of c, everything would also work out, okay? But if we replace them both with limits, then we wouldn't quite get what we want. Because we would end up with,
I think a better way to ask my question, I'm confused. Are you taking the limit as x approaches c of f of c?
Well, we do end up doing that. So when we go from this line to the next line, we do move the f of c in there, but f of c is a constant. So the limit is just itself.
Okay, that's where I was confused. Thank you.
And so the creative algebra part is you have to replace precisely one of those f of c or g of c with a limit. And you have to leave the other one alone. And then you get the magic cancellation. Okay? And I invite you can try the algebra where you take the other one as the limit, it works out, and you can try the other one, you can try both of them as the limit, and it doesn't quite work out to give you what you want. Okay? Let's see, 10 minutes, so. You can probably guess what's coming next. Yeah, let's do it. What's coming next is the chain rule. Oh, how do we want to state this? Okay, suppose I'm just going to scroll up. What do we do? We're going to need a domain. We're going to need two functions. We're going to need a cluster point. Okay. Okay, so we're going to have a domain. I'm going to do this as g of f. Okay. So f is going to map from A to the reals. Okay. But then I want to compose f with g. So I want g to map from the range of f into the reals. And I want a cluster point of A. If f is differentiable at c, and g Okay, I want to compose these things, so I'm going to be looking at g of f. So I want g to be differentiable at f of c. Okay. Then g of f is differentiable at c, and its derivative is so hopefully you remember this from Calc 1. It's the derivative of the outside times the derivative of the inside is how I always remember it. So that would be a g prime at the point f of c times the derivative of the outside, which is an f prime at c. Okay, so it's a mouthful to state. Let's see about proving it. Unless there are any questions, if there are, just feel free to interrupt me. Okay. Your book makes a big deal out of the following trick. In fact, it calls it Carathéodory's theorem. I'm just going to call it a trick that we put in the proof of the chain rule. Well, we're also going to put it in the. We're also going to put this trick in the proof of the inverse function theorem, which I guess we're going to have to look at on Monday. We're going to define the following function. Okay, I'm going to use the variable y just to keep it separate from x. Okay. What is this weird thing? Okay. Well, at any point other than f of c, this is giving us the slope of the, I think it's, if I remember correctly, it's called the secant line. The slope of the secant line from the point y, g of y, to the point f of c, g of f of c. Okay. But then, when we actually get to the point f of c, this is just giving us the derivative of g. So we're approaching that tangent line with these secant lines. Okay, we're just getting these slopes. Okay. Now, this is a continuous function. Okay. If I had more time, I would write out some steps. I would write out the explanation for that, but instead I'm just going to tell you why. Okay. At any point other than f of c, you look at what we've done up here. Well, we've taken a continuous function, g of y. It is continuous because g is differentiable. I'm sorry. I don't want to say continuous. I want to say is continuous at f of c. Okay. Yeah. I'm sorry, I claimed too much. Okay, why is this continuous at f of c? Well, at the point f of c, this function is defined to be the derivative of g at f of c. And anywhere else, it's defined to be the slope of the secant line. Well, but we know that g is differentiable at f of c. That was part of our hypotheses. And so the limit, as we approach f of c, of this slope of the secant line has to equal this derivative. Okay, that's what having a derivative means. Okay. So, and by the way, let me point out, a capital letter is a little bit unfortunate for this function because it isn't an integral. It's like a derivative. Okay. It's like the derivative of g. Therefore, we have a theorem about composing continuous functions, and it says basically you can do it. So g of little f is continuous at the point C. And now I have 1 minute left. Let me just see if we can get it done in maybe 5 minutes. Just like the proof of the product rule, we're going to work backwards from what we know it should be. So if we look at this, we know that g prime of f of c is the limit of this capital G of f of x as x approaches c. And we know that f prime is, well, I'm just going to write in the definition. Okay. Okay. Both these limits exist, as we've talked about before. One because f is differentiable, the other one because we said that capital G is continuous at the point. So I can do the product of limits thing. And I'm only going to do that at this stage. Okay, now, when we're not at the point C, we know what capital G is. So I'm going to use the definition of capital G from the above. It is G of y, which is f of x here, minus G of f of c, all over f of x minus f of c. Okay. And now I'm just going to copy down what we had for the derivative of f. I'm going to cancel two things. And I'm going to finish the proof by observing that that is the definition of the derivative of g of f of x at c. Okay, so we left one result that we didn't get to. It's the inverse function theorem. We will do that on Monday when we're also going to do the mean value theorem. Okay, so it's the end of the lecture, but I will stick around for any questions you have. So go ahead.